Welcome to our video on function transformations using tables, presented by 3MathGuys. Please subscribe and visit our website at 3mathguys.com. By now, you should know that if you take x squared and you add 3 to it, you are basically taking the entire graph and you're moving it up 3. Should you add 1 to the x before you square it, you're picking up the entire graph and you're moving it to the left 1. Now, you get some issues with this because if you have more than one transformation going on, you might have to make more than one graph just to graph the entire function. That becomes kind of tedious. Second, when we start stretching or shrinking, that causes lots of issues as well. And lastly, well, why is it that we follow the plus 3 and go up, but yet when we add 1, we're moving to the left? By the end of this video, I'm going to try to answer that question. Let's deal with the vertical shift first. Remember the parent function is x squared, which generates us this table. The function we're looking at, x squared plus 3, would generate us this table. Now, how is the table for the parent function related to the table for x squared plus 3? Well, basically, if you look at the two, the x's stay the same. But the y's, or the range, the p, is basically a change where we take the original function in black and we add 3 to all the numbers, giving us the new function x squared plus 3. This allows us to shift the function 3 units up without having to actually move the function. It's all handled in the table. Now let's look at the horizontal shift. Here you can see the graphs of our parent function in black, p of x, and the graph of our function that has been shifted to the left, x plus 1 squared, in red. And down here you can see their corresponding table of values. The one in black is clearly our parent function and the one in red is clearly our shifted function. As you can see from the graph, the vertex for the parent function is at 0, 0, and the vertex for the shifted function is at negative 1, 0. And so looking at the table, you can see how the vertex has been shifted from 0 to negative 1. Now, you can also see that all the other x values follow suit. The negative 1 moves to negative 2 moves to negative 3, and so on. This shows takes us back to the idea of, well, what are we actually doing to the parent function when we shift to the left? Similar to what we were talking about with the vertical transformations, if we look at the table of values for the parent function and we look at the table of values for the shifted function, you can see, well, the y's, they basically, or the range, it basically stays the same. But the x's, this time, we take the x's from the parent function, and what are we doing? We're basically subtracting 1 from each of them. So we can actually apply the horizontal shift to the graph before ever graphing or plotting a point by simply just subtracting 1, which leads us to this next question. Suppose we had the function x plus 1 squared plus 3, which you can clearly see is just a combination of the two functions we looked at before. There's a horizontal shift and a vertical shift. The question is the table for f of x simply the process of taking the parent function's table and then transforming them, right? If you recall, the plus 1 was a transformation where we would subtract 1 from all the x's. And the plus 3 meant that we would take all the y's and we would add 3 to them. So the question is the table for f of x simply a matter of transforming the table of p of x? Well, to get a better understanding, let's take a look at its graph. Here you can see the graph of our parent function and the graph of f of x in the red. Clearly you can see it's been shifted to the left and up 3. And you can see how the vertex has moved. Feel free to pause and write down the coordinates for this function. From the graph, we now know the table for f of x will look like this. And it is true that if you take all the x's from the parent function and subtract 1, you will get the x values for f of x. If you take all the p of x, the y values from the parent function, and add 3, you would get the y values for f of x. So it is true that basically transforming p of x will give you the table for f of x. Not one point plotted, and all transformations have been applied. Now let's explore our burning question. Why is it we do the opposite for plus 1, and yet we follow the plus 3? Remember that p of x, well, he's the parent function. And we call them parent functions because they carry basically all the major characteristics of everybody in their family. In this situation, x squared. So f of x then is really just a version of p of x. In other words, he's just a version of the parent functions. So what we're really trying to say is, what do you have to do to the parent function to create f of x? And that is what I'm going to show you right now. Let's answer the burning question first. As you recall, f of x is x plus 1 squared plus 3. The plus 3 is a shift up by 3, and the plus 1 results in a shift left by 1. Let's regroup these transformations so that what's happening to the x's stays with the x's, and what's happening to the y's stays with y's. The plus 3 clearly affects the y's, which means we need to move him. So let's go ahead and let's move him over to the other side with f of x because, well, f of x represents our y's. So to do so, simple algebra, subtract the 3, and you would get f of x minus 3 equals x plus 1 squared. Now let's answer the burning question. Why is it that we follow the plus 3 and yet we do the opposite? Well, in reality, you're not. You're supposed to be doing the opposite. In reality, when we group it so that we can see the transformations on the y's versus the transformations on the x, we know it's going to be shifted up 3, and yet it says minus 3. In this situation, clearly we knew that it was going to go to the left 1, and yet it says plus 1. So this is really what's happening here. You're not actually doing the opposite or following something. You're supposed to regroup them in terms of what's happening to the x's and what's happening to the y's. If you follow what I show you next, you'll never make the mistake again. Now, reorganizing this so that we know what's happening to the y's and what's happening to the x, we can now explore what do we do to p of x, the parent function, to get to our function f of x. So let's do it. I'm going to organize the y values together, and I know now that not only is writing it as f of x minus 3 a good way to organize your transformations, but it actually tells me if I want to get back to the parent function, I just take my f of x from my table for f of x, subtract 3 from all the y's, and I'm there. So then, what do I have to do to p of x to get to f of x? Well, that's simple. We just need to write f of x in terms of p of x. So I'm going to go ahead and add 3. And as you can see, to take p of x to f of x, all I have to do is add 3. Similarly, what do you got to do to the x's from the parent function? Well, we now know that for f of x, if I add 1 to the x's from f of x, I will get back to the parent functions. So then writing it in terms of x sub p, doing the same thing, subtract 1 off of both sides, and I now know that if I want to transform the parent function to f of x, I simply have to just subtract 1 from all my x's. This is an easier way to transform a function by just transforming the table. It doesn't seem like it right now because this is a fairly simple example, but Let's look at a more difficult one.